this video will look at issues surrounding the exchange of data and some of the methods that can be used to reduce these issues. For example, compression, encryption and hashing. So there are a range of issues relating to the exchange of data on a network. If files are too big, then we're going to use the bandwidth up, and therefore the network's going to run slowly, or certainly the online experience for the user will be slow. Secondly, security is a big problem. If you're sending sensitive data across a network, we don't want it to be intercepted and read. If it is going to be intercepted, we'd much rather it be scrambled so that it cannot be understood. So, two issues, speed and security. And we'll look at different things we can do to remedy these issues. So compression. This is where we reduce the file size, and there are reasons why we might want to do that. We might want to have less storage space. Certainly on a network we want to be able to send those files faster, and if it's less data then it can be sent quicker. And exactly the same for streaming as well. If there's less data, we can stream those files across a network much faster. And there's two ways that we can compress software. We can do lossy compression, where we're removing permanently certain data from the file to make it smaller, or lossless compression, where we temporarily remove data whilst the file is being perhaps stored or perhaps being sent across a network, and then we rebuild that data when it needs to be used again. So lossy compression, this is when, as we've already said, unrequired data is removed from a file. So think about MP3, certain frequencies that aren't noticeable, they're removed, reducing the data that the file has and not giving any real noticeable drop in sound quality. If you're chatting online via mobile phone networks, lossy compression is used to ensure that only a small amount of bandwidth is used. So when you talk on the phone, you might sound a little bit different. That's simply so that certain bits of data from that sound has been removed so that it can be sent down the wires much faster. So it's going to be using up a lot less bandwidth, and it shouldn't really affect the ability to someone to understand someone else as well. Images are often compressed using lossy compression techniques. So details of images may be lost but not impair in the overall quality. Lossy compression, especially important on websites where page load speeds can be seriously affected with image files that are large in size. So lossy compression results in much smaller files compared to lossless compression, but obviously lossless compression only temporarily removes data and therefore might be advantageous in certain situations. Okay, so lossless compression, as I just said, it only temporarily removes data. It will recreate the file later on as it was. So this type of compression might look at the sequencing of data stored within a file and construct an algorithm that can later reconstruct that file later on. And this type of compression doesn't remove as much data as lossy compression, but like I said, it does still reduce the size of the file, and more importantly, it retains the file's original data. So there's two different examples of lossless compression, different methods that we'll go through. One of them is run length encoding. So this is a simple form of lossless compression, and it demonstrates the nature of how it seeks to find patterns and sequences with data that it can reconstruct at a later date. So if you consider this pretty terrible drawing, what you will notice is that if we took the second row, okay, we've got 5 zeros in a row. Now, if we were to store that as in its original form, that would be 5 bits. 5 bits in size, that second row. But run length encoding, what it would do is it would look at the pattern of 5 white pixels in a row, and instead of storing all 5 zeros, it might say, okay, what we're going to do is we're going to store the file whilst it's compressed as 5 W's, or 101 being 5 and 0 being white, which uses 1 fewer bit. And you might think, well, that's not a huge impact at all, but that's just showing you the principle of run length encoding. So images increase in size, generally the patterns of similar shades increase in length, and so the data required to store the patterns gets much smaller in relation to the actual file's data. You know, imagine that pixel was, that picture was of, I don't know, a sky, a white sky, lots of clouds, loads and loads of white pixels all in rows. Instead of storing the data for every single pixel, you might see that there's 1,000 white pixels in a row, and run length encoding would go, okay, let's store that as 1,000 zeros. Okay, as the algorithm, 1,000 lots of 0. Okay, so much less data would be stored for that compressed file. And then later on, that knowledge that can be used to reconstruct the file as it was in its original form. So that's run length encoding. Dictionary coding is a different form, another form of lossless compression, and looks to replace the file's data with a reference to what the data is. So imagine a dictionary that contains all of the words in the English language, and imagine this dictionary was contained in a table with every word having a unique index location. For example, the word computer might be at dictionary index 24, I might be at 54, love might be at 85, science might be at location 99. So consider the following string, 23 bytes in size. I love computer science. 23 bytes because each of those characters will be a byte. So with dictionary coding, these words could be replaced with their reference, their index location in the dictionary. So the data would be stored whilst being compressed as 11000, which represents 54, which is the index location of the letter I. 110110, which is the dictionary index for 85 for the word love. And then 1010101 would be the dictionary index value 24, which represents computer, and then 11000011, which is the dictionary index 99, which references the word science. Now all of those bits added together is just 25 bits, which is far smaller than 23 bytes, so 23 lots of 8 if you like. You might be thinking, yeah, but the dictionary would have to accompany the compressed file. Yes, it would, but for large files, the size of the dictionary would have a very small impact on the overall size of the compressed file. Okay, so if you were to scale that up, the dictionary wouldn't be any bigger, but if it's a huge document that needs to be compressed, then we would see some good results. So security was another issue with exchanging data across a network. Now encryption is a way to reduce that issue. So that's where data is scrambled before being sent across a network so that it's unreadable if intercepted. So to encrypt data, an encryption key is used that will convert plain text into ciphertext, and an encryption key is an algorithm which will systematically alter each piece of data in a file. So a key might convert each letter in a text file to the next letter in the alphabet, and there's an example of that. So for the ciphertext to be converted back to plain text, either the same key or another in special cases is required by the recipient to reverse the encryption. So that's encryption, scrambling data before it's sent across a network so that if it is intercepted, it can't be read. Now for your exams, you're going to need to know the difference between symmetric and asymmetric encryption. Now symmetric encryption uses a private key. Now with symmetric encryption, the same key is used to encrypt and decrypt a file. And this means that the key also has to be passed from the sender to the recipient. And if that key is intercepted, it could be used to unravel the data that's been sent and therefore pose a security risk. So it's risky. It's straightforward, but it's risky. Now asymmetric uses a public key. So asymmetric encryption differs. You have two different keys that are used to encrypt and decrypt. One is used to encrypt the file and another is used to decrypt it. So with asymmetric encryption, the encryption key is made public. So the key to encrypt the data is made public and is used by people who wish to send you your data securely. So you make a key public and people can use that key to encrypt the data and send it to you. You, the recipient, will have your own separate private key which can be used to decrypt the file. And this is far more secure form of encryption because the decryption key cannot be intercepted. It doesn't go anywhere. So this is great if you know that if you've got data that needs to be sent to you and you want it to be encrypted, you can get other people to encrypt the data using a public key, but only you have the key to actually decrypt it. So therefore this one is much more secure. Digital signatures. So the only real possible issue with asymmetric encryption is that you could receive a file from someone which has been encrypted with your public key, but because you can't check its contents, you could decrypt it and find it to be a malicious file. So that would be not very good at all. So to ensure that you only receive legitimate files encrypted with your public key from acceptable sources, the public key can also generate a digital code or a digital signature which verifies the file content and the sender. So digital signatures are really important when it comes to ensuring that data that is being sent to you is okay. So this way you can be confident that digitally signed files contain acceptable data. Okay, hashing, another way to make sure that things are secure on networks or data being exchanged is secure. So hashing is the process of applying an algorithm on a piece of data in order to calculate a numerical value. So data is inputted, the hash algorithm will then get to work on that data and produce a numerical value. Okay, so there's nothing overly complicated about this. Don't overcomplicate it. Data goes to the hashing algorithm. The hashing algorithm looks at the data and produces a value from it. So hashing can be a really good way to encrypt data that cannot ever be decrypted. And you're probably thinking, well, what good is that? Why would we ever want to scramble data and never be able to decrypt it? Well, if you think about a password, no one should ever know a password, and it certainly shouldn't be stored on a computer system in the same form that it was inputted. So when you type in a password to create an account online, maybe you think in your head, okay, that password is going to be stored on a database somewhere in that form, and a hacker might be able to get the password. Well, that should never be the case. A password should never be stored in a database in that form. What should happen is a hash algorithm should convert an inputted password into a numerical value, which cannot be reverse engineered. It cannot be reversed. And that numerical value is then stored on file. So then when the user types their password in for their account access, the hash algorithm is performed again on that inputted data. And if the hash algorithm creates the exact same numerical value, then obviously the password that's been typed in has been typed in correctly. And the computer will be able to just compare those two numerical values, and if they are the same, then access can be granted. If not, then you won't have access to the system. So hashing allows us to basically scramble, in this case, a password into a numerical value, or convert a password into a numerical value that can be stored on the system. Every time you type in your password, it goes through the same hash algorithm. If it creates the same number that's stored on the system, it will grant you access. This is a really good way to make sure that your passwords are completely secure, because they cannot ever be read because they're not stored on the system in the form that they were written.